Hey everybody. So we're going to throw a few more limits at infinity here, right? We've looked at some rational functions, polynomials, some radicals. And this one's just kind of a hodgepodge of a few other things that are left over. They're not less important. For instance, the first one I want to talk about is one of the most important functions we have, probably, if there's a way to list functions by importance, our exponential function. Right? We want to think about what happens to this thing at infinity, or as we take the limit to infinity and the limit to negative infinity, right? So let's just take a look. We're just going to think through this idea as we make our x values larger and larger and larger, right? You can think about, it's easy to conceptualize with whole numbers, right? Of course, we can put in any exponent, but if we think about whole integers, as those integers get larger, right? So e is approximately 2.7. So if you have e to the 1, you've got 2.7. If you make x larger to say the whole number 2, 2.7 squared now is something getting close to 9, and then 2.7 cubed is up in the 20s, and 2.7 to the 4th, we're going up into the 70s, 80s, something like that. Right, as we just keep increasing the exponent, this thing gets larger and larger and larger, right? We should also remember, well, let's just say this, that we can make this as large as we want. We just take the exponent higher, right? You can name a big enough, any large number. I can tell you, it might take me a minute to figure out how large a number do I need to get that high, and I can do it, right? I can always do it. What about in the opposite direction? In the opposite direction, so to negative infinity. Well, let's kind of think through in the same way. If we have 2.7 to the negative 1, this is just 1 over 2.7. To the negative 2, we'd have 1 over 2.7 squared, 1 over 2.7 cubed, and so on and so on and so on. So these, on the positive side, these numbers are getting huge, but now we're taking the reciprocals of them because we're going in the negative direction. Negative exponents give us the reciprocal. We get huge denominators, which makes our fractions look increasingly similar to 0, right? They're just getting smaller and smaller and smaller and smaller. Okay. We can also think about this from the graph of the exponential, which we should have a good picture of, right? The graph of the exponential looks something like this, right? Off to the left, it's approaching 0. The x-axis is a horizontal asymptote, right? My drawing looks a little bit like it's curving back up there, but that's not the case. Let's see if I can rotate it a little bit. Oh, it won't let me rotate. Anyways, it's an asymptote, right? Off to the left, the function is approaching the x-axis, and on the right side, it grows without bound, right? That's one of the powers of exponential growth, and it grows incredibly quickly. As well, right? It's one of the features of exponential growth. So we get these two limits, right? And so this also applies, right? If I have something like 2 to the x, right? This same argument I made over here still works. Instead of 2.7, we have 2, and then 2 squared, and 2 cubed, and 2 fourths. These are just going to keep getting larger and larger and larger. As long as this base is something bigger than 1, we're going to get something that goes off to infinity, right? If it's 1, it just stays at 1. If it's smaller than 1, it shrinks. It's the reflection of this, okay? And so that's our exponential, right? And of course, this works for, if we do something like x to the e to the 2x, right? We can kind of just think through it in the same way. All we're doing is doubling these exponents. So in fact, it's making it even larger. We could also write something like this, e to the x squared, and one of our limit laws says that I can take the limit, do the limit of e to the x first. So we're getting larger and larger numbers, and squaring them, they're just getting larger and larger and larger, right? Any way you look at this, this thing is infinity. right? Again, and this is a way, let's remind ourselves, this is a way of saying the limit doesn't exist, but we're telling you something about the function anyways. In this case, we're telling you the function just gets ever larger. There's no cap to how large it can get. Let's look at the inverse function to the exponential. Let's look at, let's just give it its own. G of x is equal to the natural log of x. Okay, now we hopefully remember that, let's look at the graph of natural log. So it's supposed to be a reflection of this red line. I won't be able to draw it perfectly, but I'll do my best, over the line y equals x, and it looks something like this, right? And we hopefully remember, right, if we take the limit as x goes to 0, right, and in the case of the natural log, we're only going to be coming from above because it only takes positive numbers. It has a vertical asymptote that shoots down to negative infinity there, right? But what happens when we go in the other direction? When we go far away from 0, it's not entirely clear on the graph. The natural log graph gets pretty flat. And you might wonder, is it approaching some maximum value? But in fact, it's not, okay? We can always make it as large as we want, okay? We can think about the inverse of it being the inverse of the exponential, right? If we zoomed this graph out, let's do a little quick sketch. If we zoomed out, the exponential gets really steep, but it never gets perfectly vertical. Just like the natural log, it's really flat, but it's never perfectly flat. It's always increasing, right? And so just as we can always input higher and higher values for the exponential, the inverse, that means we can always get out higher and higher values for the natural log, right? Because the inputs for the exponential become the outputs for the natural log. And we know that we can put in as large a number we want for the exponential, so we can get out as large a number as we want for the natural log. And so this limit is indeed infinite. Okay. All right, let's look at another one. Let's look at x equals, the arctangent of x, the inverse tangent. Okay, let's go to a graph of the tangent to think about this function. So here's the tangent. It has asymptotes at a width of pi at starting at pi over 2. If you go to 3 pi over 2, 5 pi over 2, you just keep adding pi in both directions, we get these asymptotes, right? So the inverse, this function doesn't have an inverse unless we restrict it to a particular domain, and the domain we pick is this one in the middle between pi over 2 and negative pi over 2, right? So let's put in those lines. So here's our two vertical asymptotes. One is at x equals pi over 2. One is at x equals negative pi over 2. So there's those two asymptotes. I like to make them a little smaller and dotted. Okay, so there's our two asymptotes with our tangent in the middle. Now, when we create the arctangent, the inverse, remember graphically that means reflecting over this line y equals x. Well, when we do that, these vertical asymptotes reflected over that line become horizontal asymptotes, right? So there's the arctangent. It's that green line reflected over the line y equals x. And now we have asymptotes that are horizontal. All right, let's turn a few things off. This is getting ugly. So we'll get rid of the tangent and its asymptotes in this line. Here's the arctangent now with its own asymptotes. Those vertical asymptotes become horizontal at the same values that those horizontal or vertical asymptotes we're at. So this top one is at pi over 2, right? You can see that y coordinate's not changing. It's always pi over 2. The bottom one's negative pi over 2. So look at what's happening to our graph. As we put in higher and higher x values, we get values closer and closer to this asymptote pi over 2. And as we put in more and more negative x values, we get closer and closer to this negative pi over 2, right? We're always just above it. And so the arctangent has limits at infinity. If we make the inputs very large, this limit is pi over 2. And if we make the values, the inputs very negative, we go to negative pi over 2. Okay. Okay, there's a lot more we could talk about. There's all the different inverse trig functions. A lot of some of the inverse trig functions will have asymptotes. All the ones whose regular functions have asymptotes that are vertical, they become horizontal. But they can be handled in much the same way. We also should be able to handle some functions that when we build them out of other functions. So for instance, if I look at f of x equals 5 minus e to the x, and I want to know what happens to this thing at infinity, I'm taking the limit. I get the limit as x goes to infinity of 5 minus the limit as x goes to infinity of e to the x. Well, this first limit is just 5, and then we're subtracting this limit. What do we want to say is this limit is infinity, right? And writing 5 minus infinity is a little bit silly because we're subtracting something that can't be subtracted. But what we're really saying is this thing over here gets incredibly large. If we take away incredibly large numbers from the numbers 5, we get something that's incredibly large in the negative direction. Again, we're saying the limit doesn't exist, but the values of this function get incredibly, incredibly negative, right? And so our picture, we end up with something that, right, jumps off a cliff and just starts heading straight down pretty quickly because of that exponential, right? Off towards negative infinity. Another nonsense statement. All right, let's do one more interesting one. Here's a much more complicated function. Let's get a whole page for this. So we've got y equals 8x to the 3/2 cosine of x over x squared plus 1. And then adding 2 to it. Okay. So let's think about this function. So what do we know about cosine? Cosine is always between 1 and -1. Okay. And then let's take this expression and multiply it by, let me rewrite this function here. I can rewrite this as x to the 3/2 over x squared plus 1 times cosine of x plus 2, right? This is the same thing. I'm going to multiply both sides of this equation by 8x to the 3/2 over x squared plus 1. We know this thing is positive. Why? Because, well, x squared plus 1 is always going to be positive, right? X squared is positive, adding 1 just makes it more positive. X squared could be 0, but we're adding 1, so there's no zeros to worry about. X to the 3/2 we have to assume is taking in positive values because we got that 1/2 power in there, right? Taking a square root. So we have to be taking positive numbers. So we're only dealing with positive values of x, or 0. So we can multiply through without having to worry about flipping these or anything like that. So I multiply through and I get negative 8x to the 3/2 over x squared plus 1 is less than or equal to 8x to the 3/2 over x squared plus 1 cosine of x. And then 8x to the 3/2 over x squared plus 1. Okay. So now I know that this function not quite the function we have, but it's pinned in between these two other functions. So let's finish off by adding 2 to everything, and we get negative 8x to the 3/2 over x squared plus 1 plus 2 is less than or equal to 8x to the 3/2 cosine of x over x squared plus 1 plus 2 is less than or equal to 8x to the 3/2 over x squared plus 1 plus 2. So now I've got my original function pinned in between these two other functions. This is a setup for the squeeze theorem, right? So I'm ultimately trying to see what this function does as x goes to infinity. All right, but I don't know how to deal with this cosine. It doesn't have a limit. So I have to do something a little more clever, which is what we're setting up here, the squeeze theorem. So let's look at these functions on either side, the 8x to the 3/2 over x squared plus 1 plus 2. Let's take the limit of one of them. I'll take the one on the right, just so I don't have to deal with the negative. As x goes to infinity, of 8x to the 3/2 over x squared plus 1 plus 2, we're going to have the limit as x goes to infinity of 8x to the 3/2 over x squared plus 1 plus the limit as x goes to infinity of 2. Okay, so this part's easy, right? We know that 2 doesn't change depending on God, I'm having trouble talking. 2 doesn't change depending on the value of x. Sorry, I just lost my train of thought for a second. So this limit's easy, it's 2. Here, we're going to use some of the methods we learned before, which is looking at that highest power in the denominator and multiplying through by 1, but by writing 1 over that highest power, right? So what happens? Well, we get the limit as x goes to infinity. If I multiply 1 over x squared times x to the 3/2, I'm going to get 8 over x to the 1/2 in the numerator. In the denominator, I get 1 plus 1 over x squared. And I've still got my plus 2 out there that I already took the limit of. Well, this limit we now know how to take. 1 over x squared in the denominator becomes 0. 8 over x to the 1/2 also becomes 0 because that x to the 1/2 grows without bound. So the limit in the numerator is 0, which means the limit of this fraction is 0 since the bottom limit is 1. We get 0 plus 2 or 2. The same thing will happen on the negative side, on the side over this side over here, right? That negative won't change anything about that 0. So what is that telling us is that this thing in the middle, in the blue box, is between two things whose limits are both 2, which tells me by the squeeze theorem that this thing itself has a limit of 2, okay? So even though the cosine does some crazy things, it still has that limit. What's really happening is we have a function, 8x to the 3/2 over x squared plus 1 plus 2. The limit of that thing is 2. We've thrown cosine on one piece of it, and that just kind of toggles it. Well, let's look at a graph. It's pretty hard to explain. Let's look at a graph. Here's our function. Let's look at let's look at a copy of this without the cosine. Right, so cosine is just taking the values, at least part of the values of the black line, this first term, the 8x to the 3/2 over x squared plus 1, and multiplying them by positive or negative 1. And so where this one's up here, that portion of that is multiplied by some value of cosine. Maybe down here it's at negative 1, so it's taking this value and multiplying by negative 1. We still have the plus 2 in there, but it's bending the function as we go. But it can only do so much. It can't make it, because it's always pinned, because cosine is between negative 1 and 1, it can't push it far away from where it's supposed to be, because negative 1 and 1 just aren't that big. And so as the function gets closer and closer to 2, it's not able to push it very far because it's because of the limits on cosine. And so we see, let's go out very, very far. Let's go out to 400. Let's expand this a little bit. Let's go between -5 and 8. Whoops, oh, -52, that's why. Right, so that black line again is what would happen if we didn't have the cosine in this function. Let's also throw in the line y equals 2. We see that that black line is slowly but surely going towards that line. All the cosine does is throw in that cosine thing of vibrating around that. And so even though it's passing through the asymptote, it's still getting closer and closer to it, right? As we get further and further out, let's add some zeros. Actually, let's look at a piece between 300 and 400, or 3,000 and 4,000, or 30,000 and 40,000, right? We're so close to that line, right? So we can just, we can think about it, if we insist that the black line be close to the green line, that's the function without cosine. With the cosine will be the same closeness, will just be sometimes on the other side, but still just as close. And so we still have that limit that we see from the squeeze theorem. Okay, that is it. Just to get a few other ideas, right? We've got our big ideas for these limits at infinity, and then obviously we can do some more interesting things like in this last one. All right, that's it, everybody. Thanks. I will see you next time.